Welcome to the soothing cosmos, where the wonders of the universe unfold in calm and captivating detail. Here, we journey beyond our world, exploring the mysteries of space, the beauty of distant planets, and the secrets written in the stars. If you enjoy traveling through the cosmos with us, remember to subscribe and join our voyage across the universe. Dark matter for dummies. In the grand tapestry of the universe, there are things we can see and measure: stars shining, planets orbiting, galaxies spiraling across the cosmos. But as scientists began to study the universe more deeply, a strange and unsettling realization emerged: the cosmos is not made up primarily of the things we can see. Instead, most of it is composed of something invisible, mysterious, and almost ghost-like. This hidden substance has been named dark matter. Dark matter does not emit, reflect, or absorb light. We cannot touch it, we cannot see it directly, and yet its presence is undeniable. It outweighs all the stars and galaxies in the cosmos combined, shaping the universe itself. Without dark matter, galaxies would fly apart, stars might never have formed, and the cosmic web, the vast network of structures stretching across the universe, would not exist. In this chapter, we will take a journey through the strange and fascinating world of dark matter: what it is, how we discovered it, the theories that attempt to explain it, and why it remains one of the most important unsolved mysteries in science. The story of dark matter begins in the early 20th century. Astronomers studying the motion of galaxies noticed something strange: stars on the outer edges of galaxies were moving far too quickly. According to Newton's laws of gravity, these stars should have been flung off into space, as if spinning too fast on a merry-go-round. And yet, they remained in orbit, held in place by something unseen. The first major evidence came from Fritz Zwicky, a Swiss astronomer, in the 1930s. He studied the Coma cluster, a massive collection of galaxies, and calculated that the galaxies were moving too fast to be held together by the visible matter alone. Zwicky suggested that there must be some kind of dunkle Materie, German for dark matter, providing the missing gravity. At the time, many dismissed his idea as speculative. Decades later, in the 1970s, American astronomer Vera Rubin provided the definitive evidence. Using powerful telescopes, she measured the rotation curves of galaxies and found the same puzzling patterns Zwicky had seen: stars far from the galactic center were moving just as fast as those closer in. This could only mean one thing: galaxies were surrounded by vast, invisible halos of unseen mass. Dark matter is not ordinary matter. It is not made of atoms, protons, neutrons, or electrons, the building blocks of everything we see around us. If it were, we would detect it through the light it emits or absorbs. Instead, dark matter interacts primarily through gravity, and possibly through other forces that are still unknown. Scientists estimate that dark matter makes up about 27% of the entire universe. By comparison, normal matter, the stuff that makes up planets, stars, and humans, accounts for less than 5%. The rest is something even stranger: dark energy, a force that drives the accelerating expansion of the cosmos. But while dark energy is mysterious, dark matter has a more tangible role. It acts like the scaffolding of the universe, holding galaxies together and shaping the cosmic web. Without it, the universe as we know it would not exist. Though we cannot see dark matter directly, its fingerprints are everywhere. Scientists use several lines of evidence to confirm its existence. Galaxy rotation curves: as Rubin discovered, stars move too fast at the edges of galaxies for visible matter alone to explain their orbits. Galaxy clusters: entire clusters of galaxies are bound together more tightly than visible matter can account for. Gravitational lensing: Einstein's theory of general relativity predicts that massive objects bend light. When we observe distant galaxies, we see their light distorted by unseen mass between them and us, evidence of dark matter bending space itself. Cosmic microwave background, CMB: the faint afterglow of the Big Bang carries subtle patterns that reveal the proportions of matter in the universe. The CMB confirms that most matter must be dark. Computer simulations: models of the universe with dark matter matched the large-scale structure we observe. Without it, the universe's web of galaxies and clusters would not have formed as it did. The true nature of dark matter is one of science's biggest mysteries. Several candidates have been proposed. WIMPs, weakly interacting massive particles. For decades, WIMPs were the leading theory. These hypothetical particles would have mass but interact very weakly with normal matter, making them nearly impossible to detect. So far, no WIMPs have been found. Axions, ultralight particles that could behave more like waves than particles. They may also explain certain puzzles in particle physics. Sterile neutrinos, a theoretical form of neutrino that interacts only through gravity. MACHOs, massive compact halo objects. Early theories suggested that dark matter might simply be black holes, brown dwarfs, or other faint objects. However, evidence shows these cannot account for the majority of dark matter. Primordial black holes. More recently, some scientists have speculated that black holes formed in the very early universe could account for dark matter. So far, none of these candidates have been confirmed. Laboratories deep underground, in space, and at particle accelerators continue to search for clues. Dark matter is not just an obscure puzzle for physicists, it is central to our understanding of the universe. Without dark matter, galaxies could not form. Ordinary matter alone does not provide enough gravity to pull gas together into stars and galaxies. Dark matter's invisible halos act as seeds, enabling cosmic structures to form. The universe would look very different. Computer simulations show that without dark matter, the cosmic web would not exist, and galaxies like the Milky Way would be unstable. Physics itself may be incomplete. Understanding dark matter could reveal new forces or particles beyond the standard model of physics. Not all scientists agree on the dark matter explanation. Some alternative theories suggest that maybe our understanding of gravity itself is incomplete. Modified Newtonian dynamics, for example, proposes that gravity behaves differently at large cosmic scales. While such ideas are intriguing, dark matter remains the simplest and most consistent explanation for the evidence we have. Still, the search is ongoing, and the controversy keeps the field alive with debate. In the coming decades, new experiments may finally reveal the true nature of dark matter. Projects like the Large Hadron Collider, underground detectors in deep mines, and space observatories are all searching for dark matter particles. The James Webb Space Telescope and future missions will provide new data on galaxy formation, which may help refine our models. Meanwhile, some scientists look to the skies for natural laboratories. Collisions of galaxy clusters, like the famous Bullet Cluster, act as cosmic experiments, showing us how dark matter behaves during violent cosmic events. It is possible that the answer will come from an entirely unexpected direction, revealing new physics that changes our understanding of the universe forever. Dark matter is the invisible backbone of the universe, the silent architect of galaxies, and one of the greatest mysteries in modern science. We cannot see it, but we know it is there. It holds the cosmos together, shapes the stars above us, and may hold secrets that redefine physics itself. For now, it remains a ghost in the dark, something we feel but cannot touch, a riddle waiting to be solved. And perhaps that is what makes dark matter so captivating. It reminds us that even after centuries of discovery, the universe is still full of wonders beyond our imagination.